What if I told you that with current technology, a human could travel so far in their lifetime that when they returned to Earth, everyone they ever knew would be dead for thousands of years? Not because space is deadly, though it is, but because of a bizarre quirk in the fabric of reality itself that Einstein discovered, one that NASA engineers are already using to plan humanity's first interstellar missions. Here's the thing that's going to break your brain in the next 3.5 hours. The question, how far can we travel in a lifetime, doesn't actually have a single answer. The distance you experience and the distance Earth experiences would be radically different. We're not talking about perception or philosophy here. We're talking about cold, hard physics that's been proven in particle accelerators and atomic clocks on airplanes thousands of times. Right now, at this very moment, cosmic ray particles are screaming through our atmosphere at 99.9999% the speed of light. These particles are created in distant galaxies, and they should decay fall apart in millionths of a second. They shouldn't even make it through our atmosphere, but they do. They travel billions of miles because from THEIR perspective, their lifetime is normal, but the universe outside has slowed to a crawl. This isn't science fiction. This is happening above your head right now. And here's the absolute mind-melting part. If we could harness the same principle, and we theoretically can, a human astronaut could visit a star 50,000 light years away and come back, all within a normal human lifetime of about 80 years. But here's the catch that'll make your stomach drop. Earth would have aged 100,000 years. Your great-grandchildren, 1,000 generations down, would all be dust. Before we dive deep into this rabbit hole that's going to completely change how you think about space travel, distance, and time itself, do me a favor. Smash that subscribe button and hit the like button. This is going to be a long journey through some of the most mind-bending physics ever discovered. And I promise you, by the end, you'll never look at the stars the same way again. Also, drop a comment right now telling me what country you're watching from and what time it is where you are. I'm curious to see how far across the globe this video reaches while we talk about reaching across the galaxy. Seriously, pause and comment right now. I read every single one. All right, let's start with what seems like a simple question. How fast can humans currently travel through space? You might think the answer is straightforward. We've sent people to the moon. We've got the International Space Station zipping around up there. We know these speeds, right? The Apollo astronauts traveling to the moon reached about 25,000 miles per hour, roughly 11 kilometers per second. That's insanely fast by everyday standards. You could cross the entire United States in about 10 minutes at that speed. The International Space Station orbits at about 17,500 miles per hour. Impressive, right? But here's your first taste of how inadequate these speeds are for real space travel. At Apollo speeds, reaching the nearest star system, Alpha Centauri, which is 4.37 light years away, would take about 115,000 years. 115,000 years. The entire span of modern human civilization is only about 10,000 years old. You'd need more than 11 complete rises and falls of human civilization to reach our nearest stellar neighbor. Think of it like this. Imagine you're an ant trying to walk from New York to Los Angeles, but Los Angeles is also constantly moving away from you at a decent clip. That's not even a fully accurate analogy, because at least the ant is moving through normal space-time. We need to go so much faster. Now, here's where things get interesting. The fastest human-made object ever created isn't a spacecraft designed to carry people. It's the Parker Solar Probe, launched in 2018, which reached speeds of 430,000 miles per hour as it dove close to the sun. That's about 0.064% the speed of light. At that speed, you could get from Earth to Mars in just a few days when they're closest. Sounds amazing, right? But even at that record-breaking speed, reaching Alpha Centauri would still take about 6,700 years. We're still talking about timescales longer than all of recorded human history. So why can't we just go faster? Why can't we build a rocket that goes 1% the speed of light, or 10%, or 50%? Here's where we need to talk about the single most important number in the universe: 299,792,458 meters per second. That's the speed of light, often just written as c in physics equations. And this number isn't just a speed limit, it's woven into the very fabric of reality in ways that are absolutely bizarre. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper that would change everything. His theory of special relativity didn't just say, nothing can go faster than light. It said something far weirder. The speed of light is the same for everyone, no matter how fast they're moving. Let me explain why this is so strange. If you're in a car going 60 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the sidewalk sees that ball moving at 80 miles per hour. The speeds add up. This is common sense. This is how we expect the universe to work. But light doesn't work that way. If you're in a spaceship going 50% the speed of light and you shine a flashlight forward, you'd expect someone standing still to see that light moving at 1.5 times the speed of light. 50% plus 100% equals 150%. But they don't. They see it moving at exactly the speed of light. And here's the really weird part. You, inside the spaceship, also see it moving away from you at exactly the speed of light. This seems impossible. This seems to violate basic logic. But it's been proven true thousands upon thousands of times. Every particle accelerator on Earth operates on these principles. GPS satellites have to account for this, or they'd give you directions that are miles off. This is real. Now, Einstein realized that for this to be true for light, to always move at the same speed regardless of the observer, something else had to be flexible. And that something is time itself and space itself. They have to stretch and compress to make the math work out. This is where we get time dilation and length contraction, the two principles that are going to completely redefine what distance even means when we're talking about space travel. Here's the equation Einstein derived. If you're moving at velocity v, time for you slows down by a factor of square root 1 v squared per c squared. This factor is called the Lorentz factor, named after Hendrik Lorentz, who worked on these ideas before Einstein. At everyday speeds, this factor is essentially one time passes normally. At 10% the speed of light, time only slows by about 0.5%. You'd barely notice. But watch what happens as we push faster. At 50% the speed of light, time slows down by about 13%. At 90% the speed of light, time moves at less than half speed for you compared to the outside world. At 99% the speed of light, time is moving at about 1/7 speed. At 99.9% the speed of light, time is running at about 1/22 of normal speed. And at 99.999% the speed of light, time is running at about 1/700th of normal speed. 1 year for you equals 700 years for everyone else. This is real. This is not philosophy. And this is the key to everything we're about to discuss. Now here's what's going to blow your mind completely. And this is where we're going to start answering the actual question. Humans have already experienced time dilation. Russian cosmonaut Sergei Krikalev spent so much time on the International Space Station orbiting at high speeds that he time traveled into the future by 0.02 seconds, 20 milliseconds. He is literally 20 milliseconds younger than he would have been if he'd stayed on Earth. It's a tiny amount, sure, but it proves the principle. Time is not absolute. Your lifetime is not the same as someone else's lifetime. And if we can amplify this effect by going fast enough, really fast, the implications are staggering. But before we get to the mind-blowing destinations we could actually reach, we need to understand what happens to space itself when you're moving at these incredible speeds. because that's going to change everything about how we think about distance. Stick with me, because in the next section, I'm going to show you why astronauts traveling at high speeds would literally see the universe differently than us. The stars would move, distances would shrink, and reality itself would look alien. Okay, so we've established that time slows down when you move fast. Weird enough, right? But here's the companion effect that's equally bizarre. Distances shrink. From the perspective of someone on Earth, if you're traveling to Alpha Centauri at 90% the speed of light, you're crossing 4.37 light years of space, and it takes you about 4.85 years of Earth time to get there. But here's the thing. You, the astronaut, don't experience traveling 4.37 light years. From your perspective, because of length contraction, that distance is compressed to about 1.9 light years. Think of it like this. Imagine the universe is drawn on a rubber sheet, and as you start moving really fast, the sheet gets bunched up in front of you. The faster you go, the more compressed everything becomes in your direction of travel. The universe literally gets shorter. This isn't an illusion or a trick of perception. This is actual physical reality. Distance is not absolute any more than time is. The distance between 2 points depends on your reference frame, how fast you're moving relative to those points. At 99.9% the speed of light, that 4.37 light-year journey to Alpha Centauri shrinks to about 0.2 light-years from the astronaut's perspective. At 99.999% the speed of light, it shrinks to about 0.006 light-years, roughly 34 billion miles, which sounds like a lot until you realize that's a distance you could cross in just a few days at that speed. Now let me tell you about one of the most beautiful experiments that prove this happens. In 1971, physicists Joseph Haffel and Richard Keating took 4 atomic clocks, the most precise timekeeping devices ever created, and flew them around the world on commercial airliners, twice in each direction. These clocks were accurate to billionths of a second. When they landed and compared them to atomic clocks that stayed on the ground, the flying clocks had lost nanoseconds billionths of a second. The amount they lost matched Einstein's predictions almost perfectly. Time dilation is real. It happens at speeds we can achieve right now. It's just that at airplane speeds, the effects are tiny. But what this proves is that the principle works. And if the principle works at small scales, it works at large scales. Physics doesn't change its rules based on how convenient they are for us. Here's another mind-bending confirmation. Muons. These are subatomic particles created when cosmic rays hit our upper atmosphere about 10 kilometers up. Muons are unstable. They decay in about 2.2 microseconds on average. At nearly the speed of light, they should only travel about 660 meters before decaying. They should never reach the ground. But we detect thousands of them at ground level every second. Why? Because from the muon's perspective, traveling at 99.94% the speed of light, time is moving so slowly that its 2.2 microsecond lifespan is stretched to about 63 microseconds from Earth's perspective. Meanwhile, from the muon's perspective, the entire atmosphere is compressed to less than 700 meters thick instead of 10 kilometers. Both perspectives are equally valid. The muon reaches the ground because from Earth's view, time dilation extends its life, and from the muon's view, length contraction shortens the distance it has to travel. Now, here's where we start getting into the really exciting stuff. If length contraction is real, and if we could accelerate a spacecraft to incredibly high speeds, then from the astronaut's perspective, the entire galaxy could shrink. The Milky Way is about 100,000 light-years across. At 99.9999% the speed of light, that entire distance compresses to about 224 light-years from the astronaut's perspective. Still a long way, but now we're talking about distances that could be covered in what feels like a reasonable time frame. At 99.999999% the speed of light, Add a few more nines. The galaxy could be crossed in what feels like a few years to the astronaut. And this is a huge, but to everyone back on Earth, those journeys would still take over 100,000 years. The astronaut would come back to an Earth where everything they knew was gone, where civilizations had risen and fallen, where the human species might have evolved into something unrecognizable or gone extinct entirely. This is the trade-off. This is the cosmic deal that physics offers us. You can travel incredible distances in your lifetime, but you can never come home. Not really. Not to the same world you left. And this raises a question that should be making your skin tingle right now. If we can theoretically travel these vast distances in a single human lifetime, what's stopping us? Why haven't we done it? The answer isn't what you think, and it's both frustrating and fascinating in equal measure. But before we get to the engineering challenges, and trust me, they're insane, I need to show you exactly how far we could actually go with different speeds, because the numbers are going to shock you. We're going to map out the entire cosmic neighborhood and figure out which stars, which galaxies, which corners of the observable universe could actually be reached by a human being before they die of old age. And the answer is going to change how you think about humanity's place in the cosmos. Let's do some actual calculations. Let's figure out exactly how far a human could travel in what feels like a normal lifetime, say 40 years of travel time from the astronaut's perspective, at different speeds, approaching the speed of light. I'm going to give you a table of sorts here, but I'll walk you through it verbally. Remember, we're talking about the astronaut's experienced time, not Earth time. At 50% the speed of light, with a time dilation factor of 0.866, traveling for 40 years of your own time would get you about 17.3 light years away. That would let you reach several nearby star systems: Alpha Centauri, Barnard Star, Sirius, and a few others. Not bad, but still just our immediate cosmic neighborhood. At 90% the speed of light, with a time dilation factor of 0.436, those same 40 years would carry you about 82.6 light years. Now you can reach hundreds of stars. You could visit Vega, Altair, Fomalhaut, and many other bright stars visible in our night sky. At 99% the speed of light, the time dilation factor drops to 0.141. 40 years would let you travel about 281 light years. You could reach thousands of star systems. At 99.9% the speed of light, factor of 0.0447, you'd cover about 894 light years in 40 years of your time. You could cross a significant chunk of our local spiral arm of the galaxy. Now watch what happens when we add more nines. At 99.99% the speed of light, 4 nines, time dilation factor of 0.0141, you'd travel about 2,827 light years. You could reach the other side of our local stellar neighborhood, visit regions of the galaxy we've only ever seen through telescopes. At 99.999% the speed of light, 5 nines, factor of 0.00447, you'd cover about 8,944 light years. A huge swath of the Milky Way opens up to you. At 99.999% the speed of light, 6 nines, factor of 0.00141, you'd travel about 28,270 light years. You could almost reach the galactic center, about 26,000 light years away. At 99.9999% the speed of light, 7 nines, you'd cover about 89,440 light years in your 40 years of subjective time. You could cross the entire galaxy. And at 99.99999%, the speed of light, 8 nines, you travel about 282,700 light years. You could reach the Andromeda Galaxy, 2.5 million light years away in Earth's frame, but heavily contracted in yours. Do you see what's happening here? Every 9 we add, we multiply our range by about 3.16 times. The achievable universe expands exponentially. Here's what absolutely melts my brain about this. There is theoretically no limit to how many nines we could add. With enough nines, 99.99999999999%, the speed of light, you could cross the entire observable universe in a single human lifetime from your perspective. The observable universe is about 93 billion light years across. It seems impossibly large. But at 99.999999999999999% the speed of light, I'm not even sure how many nines that is. The entire observable universe could contract to a distance you could cross in decades from your perspective. From your perspective, you could visit the edge of everything, see galaxies forming in the cosmic dawn, witness the universe as it was just after the Big Bang, and return all before you turned 80. Of course, when you got back to Earth, the universe would have ended. The sun would have burned out. The galaxy would have dispersed. Protons themselves might have decayed. The universe would be in its heat death, cold and dark and empty. But from your perspective, you'd have done it in a lifetime. This is the most extreme possibility that physics allows. And it's real. The equations don't break down. There's no point at which the math says, no, this is impossible. The laws of physics as we understand them actually permit this. Now, let me introduce you to the concept of the achievable universe, the region of space that could theoretically be explored by a human being within their natural lifespan. For decades, physicists have worked on these calculations. One of the most thorough analyses was done by physicist Freeman Dyson in the 1960s and 70s, and later refined by others, including the physicist Edward Harrison. If we assume a maximum travel time of 40 to 50 years of subjective time, leaving some years for living at the destination, and if we could reach 99.999% the speed of light or higher, the achievable universe for a single human includes every star in the Milky Way galaxy, 100 to 400 billion stars, the entire local group of galaxies, including Andromeda, and dozens of smaller galaxies, possibly millions of galaxies beyond that, depending on exactly how fast we could go. Think of it like this. Right now, in your bedroom, or wherever you're watching this, you're sitting at the center of a sphere. If you could travel at these speeds, that sphere would encompass thousands, millions, potentially billions of galaxies, all accessible in what would feel like a normal human lifetime to you. But here's the devastating flip side. You could never share what you found with the Earth you left behind. By the time you got back from even a relatively short interstellar journey, everyone you knew would be dead. The longer the journey from Earth's perspective, the more the world would change. This brings us to one of the most profound questions in all of space exploration. If we can go, should we go? If you could visit another star system, but could never truly return home, would you go? Would you volunteer to become unstuck in time, to become a traveler between epochs, to watch everyone you love grow old and die while you remain young? We're going to come back to this philosophical question later, but first, I need to address the elephant in the room. I've been talking about what's theoretically possible according to physics, but we haven't talked about engineering. We haven't talked about how we'd actually accelerate a spacecraft to these ludicrous speeds. And when we dive into that, you're going to understand why we haven't done this yet, and why it might be the hardest thing humanity has ever attempted. Okay, reality check time. Let's talk about why, despite the physics allowing these incredible journeys, we are nowhere close to achieving them. The fundamental problem is energy. Specifically, the amount of energy required to accelerate something to a significant fraction of the speed of light is absolutely staggering, so much so that it defies easy comprehension. Let me give you some numbers. Let's say we want to send a modest spacecraft, just 1,000 kilograms, about the weight of a small car, to 10% the speed of light. How much energy would that take? Using the equation for kinetic energy, but accounting for relativistic effects, we can calculate this. At 10% light speed, we need about 4.5 times 1017 joules. That's 450,000 terajoules. To put that in perspective, that's about the total energy output of all power plants in the United States running for 3 days straight, all focused into accelerating this one small spacecraft. And that's just to reach 10% light speed. Remember our earlier calculations? At 10% light speed, reaching even the nearest star would take over 40 years. Now let's talk about reaching speeds where time dilation really kicks in. Let's say we want to reach 99% the speed of light. For our 1,000 kilogram spacecraft, we'd need about 3.3 times YP joules. That's more energy than all of human civilization uses in an entire year for one spacecraft. At 99.9% light speed, we're looking at about 1.1 times 1,020 joules, about 10 times all of humanity's annual energy consumption. And if we want to reach 99.999% light speed, where the galaxy really starts to shrink, we need about 2.2 times YA joules. That's more than 1,000 years of current global energy production, all focused on accelerating one small spacecraft. This is why we haven't done it. This is the brutal truth that science fiction often glosses over. The energy requirements are phenomenal. But here's where it gets even worse. That's just the energy to accelerate. If you want to actually stop when you get there, and you probably do, unless you want to just zoom past your destination at 99% light speed, you need roughly the same amount of energy again to decelerate. And if you want to come back, double it all again. Suddenly, you're talking about energy requirements that exceed the total energy humanity has produced in all of history, just to send one tiny probe to a nearby star and back. Now, you might be thinking, okay, but surely there are smarter ways to do this? Can't we use some clever physics trick? Absolutely. Engineers and physicists have proposed several concepts. Let me walk you through some of the most promising ones. First, the ion drive. This is technology we actually have right now. Ion drives work by accelerating ions, charged particles, to very high speeds and shooting them out the back of the spacecraft. NASA's Dawn mission used ion propulsion to visit the asteroids Vesta and Ceres. The advantage of ion drives is that they're incredibly fuel efficient. They can run for years, slowly building up speed. The disadvantage? They produce tiny amounts of thrust. The Dawn spacecraft's ion drive produced about 90 millitons of force, about the weight of a piece of paper resting on your hand. With current ion drive technology and enough time, we're talking decades of continuous acceleration. We could maybe reach 10% the speed of light. Maybe. That's actually not bad, but it's nowhere near the speeds we need for time dilation to really kick in. Second, nuclear pulse propulsion. Specifically, the Orion drive concept developed in the 1950s by physicist Freeman Dyson and others at General Atomics. The idea is wild. You literally throw nuclear bombs at the back of your spacecraft and detonate them, riding the shockwave like the universe's most dangerous surfboard. A huge plate at the back of the spacecraft absorbs the blast and transfers the momentum. The calculations suggested that with enough bombs, thousands of them, you could potentially reach 5 to 10% of the speed of light. The Project Daedalus study in the 1970s, a British interplanetary society initiative, designed a theoretical spacecraft using nuclear fusion pellets instead of fission bombs that could reach 12% light speed. The problems? Well, besides the obvious issue of detonating nuclear explosives, which is banned in space by international treaty, you'd need enormous amounts of fuel. The Daedalus spacecraft design was mostly fuel tanks, 50,000 tons of fusion fuel for a 450-ton payload. And even then, you're still in the single-digit percentages of light speed. Third, and this is where things get really interesting, beam propulsion, specifically laser sail concepts. Here's the idea, first proposed seriously by physicist Robert Forward in the 1980s. Instead of carrying fuel with you, You have a huge laser array back in the solar system that shoots an incredibly powerful beam at a lightweight sail attached to your spacecraft. The photons from the laser push on the sail, accelerating you forward. The beautiful thing about this is that you don't have to carry fuel. Your spacecraft can be much lighter. The ugly thing is that you need an absolutely enormous laser forwards calculations suggested a laser 1,000 kilometers across, putting out 65 gigawatts of power to send a spacecraft to Alpha Centauri in 40 years. But more recent proposals have gotten more refined. The Breakthrough Starshot Initiative, funded by Russian billionaire Yuri Milner and supported by physicists including the late Stephen Hawking, proposed sending thousands of tiny gram-scale probes with sails just meters across, accelerated by a 100 gigawatt laser array to 20% the speed of light. 20%. In minutes of acceleration. That's fast enough to reach Alpha Centauri in about 20 years. The Starshot Initiative is actually being developed right now. They're working on the technology. This isn't science fiction. This is active engineering. But here's the problem with laser sails for human travel. You can't carry humans on a gram-scale spacecraft. If we wanted to scale this up to carry people, the sail would need to be enormous, potentially hundreds of kilometers across. And the laser would need to be even more powerful. And there's another problem. How do you stop? The laser is back in the solar system. You're flying away from it. One proposal is to use a secondary sail that reflects the laser beam forward to slow you down. But the engineering challenges are immense. Fourth concept, antimatter propulsion. This is the holy grail of rocket propulsion. When matter and antimatter meet, they annihilate each other completely, converting 100% of their mass into energy according to Einstein's famous E equals mc. For comparison, nuclear fusion converts about 0.7% of mass into energy. Antimatter is the most energy-dense fuel theoretically possible. With antimatter, you could theoretically reach 50%, maybe even 90% the speed of light. The math works out. The problem? We can only make antimatter in particle accelerators, and it takes billions of dollars and enormous amounts of energy to create just a few nanograms of the stuff. All the antimatter ever created by humanity wouldn't be enough to boil a cup of coffee. And you'd need kilograms of it, millions of dollars worth per gram, even if we could manufacture it efficiently to power an interstellar spacecraft. So we have concepts, we have ideas. Some of them, like laser sails, are even being actively developed. But we're still decades, probably centuries, away from building a spacecraft that could carry humans to another star system at speeds where time dilation becomes significant. But here's what's absolutely fascinating, and this is where we're heading next. Even with these limitations, even with current or near-future technology, we could still potentially send humans on one-way trips to nearby stars within a single lifetime. It wouldn't be fast from Earth's perspective, but for the astronauts, with the right suspended animation technology or generation ships, it could be done. And some scientists argue we should start now, that we should launch these missions with the technology we have, because waiting for better technology means we might never go at all. In the next section, I'm going to show you exactly what these missions might look like and why they might be the most important thing humanity ever does. Let's get practical. Let's talk about what an actual human interstellar mission might look like with technology that's either current or plausibly achievable within the next 50 to 100 years. First, we need to pick a destination. Alpha Centauri is the obvious choice. It's the closest star system at 4.37 light-years away. It's actually a triple star system. Alpha Centauri A and B orbit each other, and Proxima Centauri orbits around them at a great distance. And here's the exciting part. In 2016, astronomers discovered a planet orbiting Proxima Centauri called Proxima Centauri B. It's roughly Earth-sized and sits in the habitable zone where liquid water could exist. It might be the closest potentially habitable world to Earth. So let's plan a mission to Proxima Centauri. Let's figure out what it would actually take. Mission Profile 1. The slow boat, with current chemical rocket technology, may be augmented with ion drives and gravity assists. We could potentially reach 5% of the speed of light maximum. At that speed, the journey to Proxima Centauri would take about 87 years. No human lives that long while actively traveling through space. So this mission would need to be a generation ship, a massive spacecraft carrying thousands of people who would live, reproduce, and die en route, with their descendants finally arriving at the destination. The engineering challenges are staggering. You'd need to create a completely closed ecosystem that could sustain itself for nearly a century. You'd need to generate food, recycle water and air, protect the inhabitants from radiation, maintain all systems without any possibility of resupply, and manage the social and psychological needs of isolated people who would never set foot on a planet. Research organizations like the Initiative for Interstellar Studies have studied these concepts extensively. Physicist and engineer Andreas Zialas has pointed out that the rotation of such a ship to provide artificial gravity alone presents enormous engineering challenges. The stresses on the structure would be immense, but it's not impossible. With enough resources and determination, we could build a generation ship with current technology. It would be the most ambitious engineering project in human history, but it could be done. Mission Profile 2. The Frozen Sleepers? Alternatively, instead of a generation ship, what if we could put the astronauts in suspended animation for the journey? This isn't as far-fetched as it sounds. In 2005, scientists at the Safar Center for Resuscitation research successfully placed dogs in suspended animation by replacing their blood with cold saline solution, stopping their hearts, and then reviving them hours later with no apparent ill effects. In 2019, doctors began human trials of emergency preservation and resuscitation for trauma patients. If we could extend this to years or decades, a big if, a not physically impossible, we could send astronauts to Proxima Centauri in what would feel like a very short journey to them, even if it took 87 years from Earth's perspective. You'd need automated systems to maintain the ship and wake up the crew at the destination. You'd need to solve the problem of cellular damage from long-term stasis. But again, this is engineering, not fundamental physics. It's hard, not impossible. Mission Profile 3, the laser-pushed fast track. Now let's talk about what becomes possible with near-future technology. If the Breakthrough Starshot initiative succeeds, and if we can scale up their concept to carry humans, we could potentially reach 20% the speed of light. At that speed, the journey to Proxima Centauri takes about 22 years. That's within a single human lifetime, even without suspended animation. A 30-year-old astronaut could arrive at age 52, spend years exploring, and still have decades of life left. The challenges here are different. At 20% light speed, you're dealing with relativistic effects. Time dilation becomes noticeable, though not extreme. A 22-year journey from Earth's perspective would feel like about 21.6 years to the astronauts. Small difference, but it's there. More critically, at these speeds, interstellar dust and gas become lethal projectiles. A grain of sand hits your spacecraft with the force of a bomb. You'd need massive shielding or point defense systems to vaporize debris before it hits. But physicist Robert Zubrin, founder of the Mars Society, has calculated that with a magnetic deflector shield, using powerful electromagnets to push charged particles aside and a thick frontal barrier for neutral particles, it could be done. Mission Profile 4. The fusion dream now. If we assume that within the next century or two, we'll solve the fusion power problem, which we've been working on since the 1950s, and are finally making real progress on the possibilities expand dramatically. Fusion drives could potentially reach 10 to 15% the speed of light, maybe higher. More importantly, they could sustain that acceleration for long periods, allowing for continuous acceleration to the midpoint of the journey and then continuous deceleration. This matters because constant acceleration has a beautiful side effect. It provides artificial gravity. If your ship accelerates at 1 gram Earth's gravity, the crew feels normal weight. You don't need rotating sections or other complex systems. And here's the wild part. With continuous 1 gram acceleration for half the journey and 1 gram deceleration for the other half, you can reach truly significant fractions of light speed. Physicist Philip Lubin has calculated that with continuous 1 gram acceleration, you could reach Proxima Centauri in just 3.6 years of ship time due to time dilation, even though it would be about 5.9 years from Earth's perspective. 4 years. You could visit another star system and back in less time than it takes to complete a college degree. And this is where things get really exciting, because we're not just talking about nearby stars anymore. With fusion drives and continuous 1 gram acceleration, the entire galaxy starts to open up. In the next section, I'm going to show you exactly what becomes possible with these advanced propulsion systems, and the numbers are going to blow your mind. We're talking about missions to the galactic center, to other galaxies, to regions of space that seem impossibly distant. And all of it becomes possible not in thousands of years, but in single human lifetimes. The universe is about to get a lot smaller. Here's something that will fundamentally change how you think about space travel. Constant acceleration changes everything. Let me explain why. With chemical rockets or even ion drives, you accelerate for a relatively short period and then coast. You reach your maximum speed early and maintain it. This is how we've always thought about space travel. But with advanced propulsion fusion drives, antimatter drives, or something we haven't invented yet, you could accelerate continuously throughout your journey. And this unlocks something remarkable. If you accelerate at 1 gram, exactly Earth's gravity, you'd reach 77% of the speed of light in just 1 year of ship time. After 2 years, you'd be at 97% light speed. After 3 years, 99.96%. And at these speeds, time dilation becomes extreme. The universe compresses. Impossible journeys become possible. Let me give you some specific examples that physicist William A. Edelstein calculated in his 2005 paper on relativistic spaceflight. With continuous 1 gram acceleration to the midpoint, and then 1 gram deceleration for the second half, Proxima Centauri, 4.37 light years, 3.6 years ship time, 5.9 years Earth time, Sirius, 8.6 light years, 5.0 years ship time, 10.3 years Earth time, the Pleiades cluster, 444 light years, 11.7 years ship time, 445 years Earth time, the galactic center, 26,000 light years, 20 years ship time, 26,000 years Earth time, Andromeda Galaxy, 2.5 million light years, 28 years ship time, 2.5 million years Earth time. Read those numbers again. 28 years of your life to reach another galaxy. You could leave Earth as a young adult and arrive at Andromeda before you retire. Of course, Earth would have aged 2.5 million years. The human species might not even exist anymore. The sun might have evolved into a red giant and engulfed the inner planets. But you'd only be 28 years older. Here's another mind-blowing calculation from physicist H. David Froning Jr., who worked on advanced propulsion concepts. With continuous acceleration at just 1 gram, you could cross the entire observable universe, 93 billion light years, in about 45 years of ship time. 45 years, less than a full human lifetime. You could visit the edge of everything we can see. Look back at the cosmic microwave background radiation from the Big Bang itself, and you'd only be middle-aged. When you tried to return, you'd find that the universe had aged 93 billion years longer than its current age. The universe would be in deep heat death. All the stars burned out, all the black holes evaporated through Hawking radiation. Nothing would remain but photons and particles drifting apart in the eternal darkness. But from your perspective, a long trip, sure, but just a normal human lifetime. This is what Einstein's equations allow. This is what the laws of physics actually permit. Now, you might be wondering, how much energy would this require? How much fuel would you need to maintain 1 gram acceleration for years? The answer is, a lot. A terrifying amount. For a 1,000-ton spacecraft, pretty modest for a human mission, to maintain 1 gram acceleration for 1 year, you'd need to convert about 4.3 tons YOI joules of energy into thrust. Over the course of a 20-year journey to the galactic center, you'd need about 8.6 times YP joules total. That's roughly equal to the total energy output of the sun for about 1 second, or all of human civilization's energy consumption for about 5,000 years. Where would this energy come from? With fusion, you'd need about 300,000 tons of hydrogen fuel, assuming 100% efficiency, which is impossible. Real fusion drives might only be 60 to 70% efficient, so add more fuel. With antimatter, you'd need only about 3,000 kilograms, due to the perfect mass-energy conversion. But remember, we can't make antimatter in useful quantities yet. There's another concept worth mentioning, the Bussard ramjet, proposed by physicist Robert W. Bussard in 1960. The idea is brilliant. Instead of carrying fuel, you scoop up hydrogen atoms from interstellar space using a huge electromagnetic field, potentially thousands of kilometers across, and use them for fusion fuel as you go. It's like flying a jet airplane that scoops air for its engines, except you're scooping hydrogen from space for fusion. And mathematics suggests this could work up to about 12% the speed of light. Beyond that, the drag from collecting the hydrogen would exceed the thrust you get from burning it. But there are problems. Interstellar space is incredibly empty, about 1 hydrogen atom per cubic centimeter on average. To collect enough, you'd need a truly enormous collector field. And fusion is hard. We haven't even achieved sustained fusion on Earth yet, let alone in a spacecraft. Still, the Bussard ramjet remains a fascinating concept that physicists continue to refine. So we have the physics. We have concepts for propulsion systems. We can map out specific journeys with specific timescales. On paper, humans really could travel across the galaxy, even to other galaxies, within their natural lifetimes. But there's a question we haven't addressed yet, and it's one that keeps me up at night. What would these journeys actually feel like? What would you see looking out the window of a spacecraft, traveling at 99.99999% the speed of light? How would the universe look different? And what psychological toll would it take to know that every second you travel, years or centuries are passing on Earth? In the next section, we're going to step inside the spacecraft and experience what relativistic travel would actually be like. And I promise you, it's weirder than anything you've imagined. Imagine you're inside a spacecraft accelerating toward the galactic center at 1 gram. For the first few months, things seem relatively normal. You feel weight. Your acceleration provides artificial gravity. You can walk around, exercise, live relatively normally. But as you approach significant fractions of the speed of light, reality starts to get weird. First, there's aberration, the apparent shifting of star positions. As you accelerate, the stars in front of you start to crowd together in your field of view. Stars that were far apart appear closer together. Meanwhile, stars behind you spread out and eventually disappear from view entirely as your spacecraft outpaces their light. By the time you reach 90% light speed, almost all the stars you can see are squeezed into a circle directly in front of you, maybe 30 degrees wide. The rest of the sky is black. You're literally seeing the universe compressed by your velocity. Then there's the Doppler shift. Light from stars in front of you is blue shifted, compressed to higher energies. Stars behind you are red shifted, stretched to lower energies. At extreme velocities, this becomes dangerous. Visible light from stars in front shifts into ultraviolet, then X-rays, then gamma rays. The gentle starlight becomes deadly radiation. You'd need heavy shielding on the front of your spacecraft. Meanwhile, light from behind shifts all the way into the radio spectrum and effectively becomes invisible. The cosmic microwave background radiation, the afterglow of the Big Bang, normally at about 2.7 Kelvin would be blue shifted in front of you to potentially dangerous levels. Physicist John D. Barrow calculated that at speeds very close to light speed, the accumulated blue-shifted cosmic microwave background radiation could create a radiation field intense enough to damage or destroy your spacecraft. There's literally a radiation wall in front of you created by your own velocity. Here's another weird effect. Time itself becomes visible. Because light takes time to reach you, when you look at a distant object, you're seeing its past. Normally, this doesn't matter much. The Andromeda Galaxy is 2.5 million light-years away, so we see it as it was 2.5 million years ago. But the difference between now and then is academic. But when you're traveling at relativistic speeds, this creates a bizarre situation. As you accelerate toward a distant star or galaxy, you're literally fast-forwarding through its timeline. If you travel to a star 1,000 light-years away at near-light speed, you'd watch it age 1,000 years during your journey, all compressed into the few years it takes you to get there from your perspective. You'd literally see time passing in fast-forward. Stars would visibly move in their orbits. You might watch a star be born, live its life, and explode as a supernova all during your journey. The universe becomes a time-lapse photograph. Now let's talk about communication. This is where things get heartbreaking. Imagine you're on a journey to Proxima Centauri at 90% light speed. The journey takes about 6.5 years from your perspective. You want to stay in touch with Earth, send updates, receive news from home? But here's the problem. You're moving away from Earth at 90% light speed. Radio signals you send back are redshifted and time-dilated. A message you send that takes you 1 minute to broadcast would be received on Earth stretched out over several minutes and redshifted to lower frequencies. Meanwhile, messages from Earth to you are blue-shifted and compressed. An hour-long message from home might be received as a minutes-long, high-pitched squeal that needs to be processed to be understood. And there's the delay. Even at light speed, messages take time. By the time Earth's response to your first message reaches you, you're already at your destination. Realistically, there would be no real-time communication. You'd send status updates into the void, knowing they wouldn't be received for years. You'd receive messages from an Earth that was already years in the past. The psychological implications are staggering. Psychologist Nick Conness, who studied isolation in Antarctic research stations and on the International Space Station, has pointed out that the single biggest stressor for isolated people is feeling disconnected from home and loved ones. On the ISS, astronauts can see Earth out the window. They can communicate in real time. They know they're coming home in a few months. On an interstellar voyage, you can't see Earth. It's a dot lost among billions of stars. You can't communicate meaningfully. And you know that if you return, everyone you knew will be dead. Some researchers have suggested that the crews for such missions would need to be fundamentally different psychologically from normal humans. Perhaps people who are naturally more isolated, less social, more comfortable with solitude. Or perhaps we'd need to fundamentally restructure the social dynamics of the mission, creating new forms of community and connection aboard the ship itself. But here's something that gives me hope, something beautiful in all this strangeness. You wouldn't be alone. Every person on that spacecraft would be going through this experience together. You'd be a community unstuck in time, travelers between epochs, witnesses to the universe in a way no humans have ever been. And you'd have a purpose, a mission, to reach out and touch another world, to expand the sphere of human knowledge and presence, to ensure that some part of humanity survives, even if Earth itself falls to catastrophe. In the next section, we need to confront the biggest question of all. Why would anyone go? What could possibly motivate someone to leave behind everything they know for a journey into the unknown? The answers might surprise you because they reveal something profound about human nature itself. Why would anyone volunteer for a journey they can never return from? Why would you board a spacecraft knowing that everyone you love will die while you're gone? That the world you return to, if you return, will be as alien to you as another planet? Let's start with the obvious answer: exploration and discovery. Throughout human history, people have risked everything, even their lives, to see what lies beyond the next horizon. Polynesian sailors ventured into the Pacific Ocean without knowing if they'd find land. European explorers crossed oceans. Mountain climbers scale peaks that might kill them. Why? Because it's there. Because they need to know. Astronaut Chris Hadfield, who commanded the International Space Station, once said in an interview that he'd volunteer for a one-way mission to Mars without hesitation. When asked why, he said, "Because I'd get to see something no human has ever seen. I'd get to learn things no one has ever known. That's worth everything to me." But there are other motivations, and some of them are darker, more practical. Consider this. We live on a single planet. One asteroid, one supervolcano, one nuclear war, one pandemic. Any of these could end human civilization, or even the species itself. The physicist Stephen Hawking argued repeatedly before his death in 2018 that humanity's long-term survival depends on becoming a multiplanetary species. He suggested we have perhaps 100 to 200 years to establish permanent settlements beyond Earth or face potential extinction. From this perspective, interstellar missions aren't just about exploration. They're about survival. They're about ensuring that some humans, somewhere, survive even if Earth is destroyed. Anthropologist Cameron Smith at Portland State University has studied the genetics and demographics of interstellar colonization. He calculated that a minimum viable population for a generation ship would be about 10,000 to 40,000 people to maintain genetic diversity and social stability over multiple generations. That's a lot of people, but if it means saving the species, absolutely worthwhile. There's another motivation: ideology and belief. Throughout history, people have traveled to distant lands to establish new societies based on their principles. The Pilgrims sailed to America. Mormons trekked to Utah. Countless groups have sought to create utopias away from the constraints of existing societies. Interstellar travel offers the ultimate fresh start. A whole new world, light years from Earth, where you could build a society from scratch based on any principles you choose. Want a world dedicated to scientific research, free from political constraints? A libertarian paradise with minimal government? A religious community? A post-scarcity socialist utopia? An experimental society testing radical new ideas about governance, economics, or social organization? On a colony world around another star, separated by years of travel time from Earth, you'd have the freedom to try. You could experiment with forms of society that would never be permitted on Earth. Sociologist Marshall Savage, in his book, The Millennial Project, argued that this diversity of human societies across different worlds would be humanity's greatest strength, ensuring that if one approach fails, others might succeed. And then there's the personal motivation that I think is most powerful: legacy. Imagine being one of the first humans to set foot on a planet orbiting another star. Your name would be in history books, not just for decades or centuries, but for as long as human civilization exists. You'd be alongside the first person to walk on the moon, the first to reach the North Pole, the first to circumnavigate the globe. But more than fame, you'd be part of something that matters on a cosmic scale. You'd be expanding the light of consciousness into the universe. You'd be ensuring that life, this rare, precious thing that we know exists on Earth and might exist nowhere else, spreads and persists. Philosopher and writer Carl Sagan often spoke about how we're the universe's way of knowing itself. We're the consciousness that emerged from matter, the eyes through which the cosmos looks back at itself. By traveling to other stars, by bringing life and thought to dead worlds, we're fulfilling what might be our deepest purpose: making the universe aware of itself, transforming it from a cold mechanical system into something that knows, that feels, that understands. There's one more motivation I want to mention, and it's the one that hits me hardest: the knowledge that you'd gain. Think about what those travelers would learn. They'd see planets that no human has ever seen. They'd discover life forms, if they exist, that evolved completely independently from Earth life. They'd witness phenomena we can only theorize about. But beyond that, they'd gain philosophical knowledge that's impossible to obtain on Earth. By experiencing time dilation firsthand, by watching the universe age and fast forward, by becoming unstuck from the normal flow of time, they'd understand the nature of reality in a way that we earthbound humans simply cannot. They'd be the only humans who truly, viscerally understand that time is not absolute. That simultaneity is an illusion, that the universe is far stranger than our everyday experience suggests. That knowledge, that perspective that's precious beyond measure. So there are motivations: curiosity, survival, ideology, legacy, knowledge. Plenty of reasons why someone might go. But we need to flip the question now. Instead of asking why individuals would go, we need to ask, why would humanity as a whole invest in sending them? What's in it for us, the people who stay behind? Because here's the thing. Even if we can't benefit directly from these missions, even if the travelers never return with anything useful to those who funded their journey, I'm going to argue that these missions might be the most important thing we could do. And the reasons why reveal something profound about what it means to be human. Here's a perspective that might surprise you. Some scientists argue that we should launch interstellar missions now with the technology we have today, even if better technology is just decades or centuries away. This seems counterintuitive. Why send a slow generation ship that takes centuries to reach its destination, when, if we just wait, we could send a fast fusion ship that gets there in decades? The answer is called the weight calculation, or sometimes the interstellar weight problem. And it was first seriously analyzed by Andrew Kennedy in a 2006 paper. Here's how it works. Imagine our technology is improving steadily. Let's say we can currently send a ship to Alpha Centauri that would arrive in 100 years. But if we wait 50 years, we'll have better technology that could get there in 50 years. Should we wait? Well, if we wait 50 years and then launch, the total time until humans reach Alpha Centauri is 100 years. 50 years waiting plus 50 years travel. That's the same as launching now. We gain nothing by waiting. But wait, what if technology improves faster? What if in 30 years, we could send a ship that arrives in 10 years? Then the total time is only 40 years, versus 100 if we launch now. We should definitely wait. Kennedy analyzed this mathematically and found that there's a sweet spot. If technology is improving at a certain rate, there comes a point where waiting no longer helps, where the reduction in travel time from better technology is offset by the time spent waiting. His calculations suggested that for most reasonable assumptions about how fast space technology improves, we're already past that point, or will be within the next few decades. In other words, we should launch soon, not wait for perfect technology that might never come. But there's another argument for going now, and it's more philosophical. Physicist and author Freeman Dyson pointed out that civilizations don't last forever. Rome fell, Egypt declined. Even the British Empire, on which the sun never set, faded. There's no guarantee that human civilization will keep progressing. We could face catastrophic setbacks: nuclear war, pandemic, environmental collapse, asteroid impact. We could enter a dark age where technology is lost and takes centuries to rediscover. If we wait for perfect technology, we might wait forever. But if we go now with what we have, then we've actually done it. We've actually planted the seeds of humanity among the stars. Dyson argued that a single generation ship that successfully establishes a colony on another world would be worth more in the cosmic long run than all the wars, politics, and economics happening on Earth. It would be the one thing from our era that mattered on thousand-year timescales. There's also an economic argument, though it's subtle. Economist Robin Hanson has analyzed the economics of space colonization and reached a surprising conclusion. The first colonies will probably not be established for profit or resources. They'll be established for ideology, for insurance against extinction, for scientific knowledge, or simply because we can. But once established, those colonies become independently valuable. They develop their own economies, their own innovations, their own reasons for existing. And over time, they may produce things that Earth needs or wants. Not physical resources, it's too expensive to ship things between star systems, but information, ideas, solutions to problems. A colony world dealing with different conditions would develop different technologies, different social structures, different ways of thinking. That diversity itself becomes valuable. It's the same reason why biological diversity is valuable in ecosystems. It provides resilience and innovation. Here's another consideration. By sending out colonies, we increase the chance that something of humanity survives long term. Astronomer Martin Rees, Britain's Astronomer Royal, wrote a book called Our Final Hour, in which he estimated that humanity has only a 50% chance of surviving the next 100 years without a major catastrophe. He's not talking about extinction necessarily, but about a collapse that sets us back significantly, perhaps so far back that we never recover to the point of being able to attempt interstellar travel again. If that's true, then the window for getting off this planet might be shorter than we think. We might only have this century or the next to actually do it before the opportunity closes, maybe forever. From that perspective, every decade we delay is a decade of risk. We're betting that nothing catastrophic will happen before we're ready. History suggests that might be a bad bet, so the case for going now is actually pretty compelling. Technology might not improve fast enough to justify waiting. Civilizations can collapse, and we're taking a risk every year we delay. But there's a counter-argument, and it's powerful. We might be completely wrong about what's possible. In the next section, I'm going to blow your mind with some of the more exotic physics that could make interstellar travel even easier or might make it completely unnecessary. We're talking about wormholes, warp drives, and whether the laws of physics might have loopholes we haven't discovered yet. Buckle up, because we're about to go from solid science into the realm of maybe, possibly, we're not sure yet. Physics. Everything I've told you so far is based on physics we know is true, confirmed by experiment. Time dilation is real. Length contraction is real. The speed of light limit is real. But physics is not complete. We know this because quantum mechanics and general relativity, our two foundational theories, are incompatible with each other at extreme scales. There's physics we don't understand yet, and in that gap in our knowledge, there might be loopholes, ways to travel faster than light without actually violating relativity. Let's explore some of them. First, wormholes. In 1935, Einstein and his colleague Nathan Rosen discovered a mathematical solution to general relativity that suggested shortcuts through space-time could exist later called Einstein-Rosen bridges or wormholes. Here's the concept. Instead of traveling through normal space from point A to point B, you could take a shortcut through a higher dimension. Think of it like this. If space is a sheet of paper, the normal route from one edge to the other crosses the whole sheet. But if you fold the paper so the edges touch, you can poke a hole through and step across. Wormholes, if they exist and could be kept stable, would allow faster-than-light travel in the sense that you'd arrive at the destination faster than a light beam, taking the normal route through space. But you wouldn't actually be moving faster than light. You'd just be taking a shorter path. The problem? Keeping a wormhole open requires something called exotic matter with negative mass energy. We've never observed anything like this. It might not exist. Physicist Kip Thorne, who won the Nobel Prize for his work on gravitational waves, analyzed wormholes mathematically and concluded that while they don't violate any known laws of physics, the amount of exotic matter needed to stabilize even a small wormhole would be enormous, potentially more mass energy than exists in the entire solar system. And there's another problem. Wormholes could create time travel paradoxes. If you could travel through space faster than light, you could, under certain circumstances, arrive before you left from another observer's perspective. This creates all kinds of causality problems. Most physicists think wormholes are probably impossible for practical use, but we can't rule them out entirely. They remain an intriguing theoretical possibility. Second, the Alcubierre warp drive. In 1994, physicist Miguel Alcubierre published a solution to Einstein's field equations that would allow faster-than-light travel without violating relativity. The idea: instead of moving through space, you warp space itself. You contract space in front of your ship and expand it behind you, creating a warp bubble that carries you along. From outside, the bubble moves faster than light. But inside the bubble, you're not moving at all. Space is moving around you. Think of it like a surfer riding a wave. The wave moves faster than the surfer can swim, but the surfer isn't moving through the water. They're being carried by the wave itself. The math works. The equations are consistent with general relativity. There's no theoretical reason it can't work. And this is a big, but the Alcubierre drive has the same problem as wormholes. It requires exotic matter with negative mass energy. A lot of it? Alcubierre's original calculations suggested you'd need the mass energy equivalent of Jupiter, converted to exotic matter to create a warp bubble. Later refinements by physicist Harold White at NASA reduced this to maybe the mass of a spacecraft, like Voyager's still exotic matter, which we can't produce. White and his team at NASA's Johnson Space Center actually researched this seriously in the 2010s under the Advanced Propulsion Physics Laboratory program. They tried to detect tiny warp fields in the lab. They found nothing conclusive, but the fact that NASA took it seriously enough to fund research is fascinating. There's also a problem physicist William A. Hiscock pointed out. As you accelerate to warp speed, you'd accumulate blue-shifted radiation in front of your warp bubble. When you decelerate, all that radiation would be released in a devastating burst that could destroy anything in front of you, including your destination. So even if we could build a warp drive, using it might be dangerous. Third, quantum tunneling on macroscopic scales. In quantum mechanics, particles can tunnel through barriers they shouldn't be able to cross according to classical physics. An electron can appear on the other side of a barrier without having traveled through it. This is real, confirmed, everyday physics. Quantum tunneling is why radioactive decay happens, why the sun can fuse hydrogen at temperatures that shouldn't be hot enough, why flash memory in computers works. But could it work for large objects? Could a spacecraft quantum tunnel across light years of space? Almost certainly not. The probability of tunneling drops exponentially with the mass and distance involved. For something the size of a spacecraft tunneling across even a meter, the probability is so low that you'd need to wait longer than the age of the universe for it to happen, even once. But here's the fascinating thing. The probability isn't exactly zero. It's just unfathomably small. Physicist Frank Wilczek, who won the Nobel Prize for his work on quantum chromodynamics, has pointed out that in a truly infinite universe with infinite time, every possible quantum event eventually happens, including ridiculously improbable ones. So could a spacecraft spontaneously tunnel to Alpha Centauri? In an infinite universe, eventually, yes. But waiting for it to happen is not a viable strategy. Fourth, and this is the really wild one, manipulating the constants of physics. The speed of light, c, is a constant in our current understanding. But some theories suggest that the constants of physics might have been different in the early universe and might be slightly different in distant regions of space. If we could somehow manipulate the local value of phi, make it higher in the region around our spacecraft, then we could travel faster while still respecting a local speed limit. This is pure speculation. We have no idea how to do this, or even if it's possible in principle. But it's not ruled out by any physics we know. Physicist João Magalhães has worked on theories of varying speed of light and found they're mathematically consistent with general relativity. They might even explain some cosmological observations better than standard theory. But again, this is frontier physics. It's not established. It might be wrong. So we have exotic possibilities. Wormholes, warp drives, quantum tunneling, variable constants of physics. All of them are either impossible with current understanding or require technology so far beyond us that they might as well be magic. But here's the thing. Every one of these ideas comes from serious physicists working within established frameworks. They're not making things up. They're following the math and seeing where it leads. Does that mean we'll ever build a warp drive or open a wormhole? Probably not. But a century ago, we thought heavier-than-air flight was impossible. 50 years ago, we thought computers that fit in your pocket were impossible. We're not great at predicting what future technology will achieve. In the next section, we need to confront something more grounded but equally profound: the philosophical implications of interstellar travel. What does it mean for humanity if we spread to the stars? What do we gain, and what do we lose? And how should the possibility of space travel change how we think about our lives right here and now on Earth? Let's zoom out and think about what interstellar travel really means for humanity as a whole. Right now, every human who has ever lived, all 100 billion of us throughout history, has lived on one planet, orbiting one star. Our entire civilization, every empire, every work of art, every scientific discovery, every war, every love story, all of it happened in a tiny region of space, smaller than a speck of dust in the cosmic scale. Interstellar travel would change that fundamentally. For the first time, humans would exist in multiple star systems. We'd become a multi-stellar species. But here's the profound part. Those humans would be fundamentally separated from us, not just by distance, but by time itself. Because of time dilation and the sheer distances involved, different human colonies would age at different rates. A colony near a massive black hole would experience time differently than one in empty space. Travelers moving between colonies would age differently than those who stay put. Humanity would splinter into separate timelines, separate reference frames, separate realities that only occasionally intersect. Philosopher and cosmologist Nick Bostrom has written about how this could lead to the development of separate species of humans over time. Not just culturally different, but biologically different, adapted to their environments and separated by millions of years of subjective time. In a million years, descendants of Earth humans living on 100 different worlds might be as different from each other as we are from Homo erectus. They'd all trace their lineage back to Earth, but they'd be separate species. Is that still humanity? Or is it something new? There's another philosophical question: the problem of personal identity across time. Imagine you're 30 years old and you leave on an interstellar journey. You travel at near light speed for what feels like 10 years to you. You arrive at your destination, spend 10 years there, and return. To you, 30 years have passed. You're now 60 years old. But on Earth, 10,000 years have passed. The language you speak is dead. The nations you knew are gone. The species you left behind has evolved. Nothing you knew exists anymore. Are you still the same person? You have continuity of consciousness, continuity of memory, but you have no continuity of context, of society, of connection to anything outside yourself. Philosopher Derek Parfit argued that personal identity is largely constituted by psychological continuity and connectedness to others. By that standard, the returning traveler would have lost their identity, even though they're physically the same person. You'd be a ghost, a living anachronism, a person whose entire world existed only in the past. But flip it around. Maybe that's liberating. You'd be free from all the constraints of your origin, free from the expectations of society, from the weight of history, from the assumptions about who you should be based on where you came from. You could reinvent yourself completely. You'd be unbounded by anything except your own choices. Science fiction author Ursula K. Le Guin explored this in her novel, The Dispossessed, where interstellar travelers become ambassadors between radically different societies, belonging fully to neither, but carrying ideas between them. Maybe that's what interstellar travelers become, ambassadors of humanity across time, carriers of culture and knowledge between epochs, bridges connecting past and future. Here's another implication that fascinates me. Interstellar travel forces us to think on truly long timescales. Right now, most human planning operates on scales of years or decades. Corporations plan quarterly. Politicians plan election cycles. Even our grandest projects, building a cathedral, developing a technology, rarely think beyond a century. But interstellar travel demands thinking on scales of thousands or millions of years. A generation ship project would need to plan for the survival and well-being of people who won't be born for centuries. A colony world needs to think about sustainability and adaptation over geological timescales. This kind of thinking could transform how we approach problems on Earth. Climate change operates on century timescales. Species conservation operates on millennial timescales. If we develop the capacity to think and plan on interstellar timescales, we might finally address these long-term challenges. Philosopher Roman Krasznarek has written about long-term thinking and how cultivating it could help solve many of humanity's problems. Interstellar travel might force us to develop exactly this capacity. There's also a profound shift in how we think about life and death. Right now, death is final. When you die, you're gone, and within a few generations, you're forgotten except by historians. But if humanity spreads across the stars and persists for millions of years, then you personally, watching this video, are part of the lineage that leads to that vast cosmic future. Your choices, your contributions, your DNA, your ideas, they ripple forward through time. You're not just a temporary blip. You're part of an unbroken chain connecting the primordial soup to the heat death of the universe. Philosopher Brian Greene discusses this in his book, Until the End of Time, arguing that even though individuals die, the patterns we create in our genes, our cultures, our ideas can persist essentially forever. If humanity becomes a star-faring species, then every human becomes immortal in this sense. We all become part of something that transcends our individual lifespans. These philosophical implications are profound, but they might seem abstract. In the next section, I want to bring this back to you personally. How should the possibility of interstellar travel change how you think about your own life? What does it mean for you right now that humans could potentially travel across the galaxy in a single lifetime? The answer might change how you see your place in the universe. It might change what you think is important. And it might fill you with a sense of wonder and purpose that you've been missing. Stay with me. All right, we've covered the physics, the engineering, the philosophy. Now let's talk about what this means for you, personally, watching this video right now. First, a reality check. You're probably not going to travel to another star system in your lifetime. The technology doesn't exist yet, and it probably won't exist for decades or centuries. But here's what you need to understand. You are living in the era when humanity is figuring this out. You are alive during the transition from a single planet species to a potentially multi-stellar civilization. Think about that for a moment. In all of human history, spanning hundreds of thousands of years, this transition will happen exactly once. And it's happening now, in your lifetime. You are living through one of the most significant moments in not just human history, but in the history of Earth life itself. Life has existed on Earth for 3.8 billion years. For all but the last century of that time, it was confined to one planet. Now, for the first time, life is developing the capacity to spread beyond its home world. You are witnessing this. You are part of this. When historians billions of years from now look back at the arc of Earth's story, this era right now will be marked as one of the crucial turning points. The moment when life escaped its cradle, and you're here for it. But beyond just witnessing it, you can contribute to it. You don't have to be an astronaut or a physicist. The transition to a spacefaring civilization requires millions of people working on millions of different problems. We need engineers designing better propulsion systems. We need biologists figuring out how to grow food in space. We need psychologists understanding how to maintain mental health during long isolation. We need artists and writers helping us imagine what these future worlds might be like. We need ethicists working through the moral implications. We need politicians building the international cooperation needed for these huge projects. We need everyone. Whatever your skills, whatever your interests, there's a way to contribute to humanity's expansion into the cosmos. Here's something else. Even if we never achieve interstellar travel, the attempt itself is worthwhile. The Apollo program, which landed humans on the moon, generated enormous technological spin-offs. Improved computers, new materials, medical advances, satellite technology. These spin-offs arguably contributed more to human well-being than the moon landings themselves. The push toward interstellar travel would drive innovation in energy generation, materials science, biology, artificial intelligence, and dozens of other fields. These innovations would improve life on Earth, even if we never leave the solar system. Fusion power research, for example, is motivated partly by space travel needs. If we crack fusion for spacecraft, we solve Earth's energy needs forever. Life extension research is motivated partly by the need for astronauts to survive long journeys. If we extend human lifespan for space travel, we extend it for everyone. There's also something deeply meaningful about having a long-term goal as a species. Right now, a lot of human effort goes into conflicts. Nation against nation, ideology against ideology, corporation against corporation. We fight over resources, over territory, over whose vision of society should prevail. But interstellar travel is a goal that transcends these conflicts. It's big enough that it requires global cooperation. It's long-term enough that it dwarfs the time span of political disputes. It's ambitious enough that it could unite humanity in a common purpose. Carl Sagan called this the cosmic perspective. When you look at Earth from space, borders disappear. National conflicts seem petty. We're all just humans on a tiny world, surrounded by vast and indifferent cosmos. Working toward becoming a spacefaring species could give us that perspective without having to literally go to space. Here's the most personal part. Thinking about interstellar travel can change how you think about your own life. When you understand that time is not absolute, that different observers can experience reality differently, that the universe is far stranger than our daily experience suggests, it shifts your perspective. Your problems, your stresses, your anxieties, they're real and valid, but they're also temporary and local. They exist in one tiny slice of space-time, in one reference frame among infinite possibilities. This isn't about making your problems seem small or insignificant. It's about seeing them in context. You're part of something vast and ancient and ongoing. Your life is a brief flash, yes, but it's a flash that contributes to the grand tapestry of cosmic evolution. And here's what gives me chills. Everything that exists, every atom in your body, every thought in your mind came from the stars. The hydrogen that makes up 60% of your body was forged in the Big Bang itself. The heavier elements, the carbon in your DNA, the calcium in your bones, the iron in your blood, were created inside stars that exploded billions of years ago. You are literally made of star stuff, as Carl Sagan famously said. And if humanity becomes a spacefaring species, we complete the circle. The atoms that came from stars will return to stars, will spread across the galaxy, will seed new worlds with life and consciousness. You are part of that story. You are part of the universe's way of organizing itself into higher and higher levels of complexity and awareness. That matters. That means something. So what should you do with this knowledge? First, maintain a sense of wonder. Never lose the awe you feel when you look up at the night sky and realize those points of light are entire suns, potentially with their own worlds, their own stories. Second, support space exploration however you can. Vote for politicians who fund it. Donate to organizations working on it. Choose careers that contribute to it. Or just talk about it, share it, help others understand why it matters. Third, think long-term. Make choices that benefit not just you or your children, but the version of humanity that will exist centuries or millennia from now. And fourth, remember that we are all, every one of us, on a journey through space-time. You're traveling through the universe right now at incredible speeds as Earth orbits the Sun, as the Sun orbits the galaxy, as the galaxy moves through the cosmic web. You're already in space traveler. You just don't usually think of it that way. In our final section, I want to bring everything together. I want to answer the title question definitively. How far can humans actually travel through space in one lifetime? And I want to leave you with a vision of what our cosmic future might hold if we're brave enough to reach for it. So, how far can humans actually travel through space in one lifetime? The answer, as you now understand, is it depends on whose lifetime you're measuring. From Earth's perspective, a human lifetime is roughly 80 years. In that time, you can't go far. With current technology, maybe to Mars and back. With near-future technology, perhaps a slow flyby of the outer planets. But from the traveler's perspective, everything changes. With constant 1-gram acceleration, using fusion or antimatter drives technology, that's possible in principle, if not yet in practice. You could reach the nearest stars in a few years, across the galaxy in 20 years, to nearby galaxies in 30 years, to the edge of the observable universe in 45 years. All of this is real. All of this is permitted by the laws of physics as we understand them. Of course, there are caveats. We don't have the propulsion technology yet. We don't have the energy sources. We don't know how to protect astronauts from radiation for decades. We don't know if the human psyche can handle such journeys. But none of these are fundamental limits. They're engineering challenges. They're hard, perhaps the hardest things we've ever attempted, but they're not impossible. The universe is not closed to us. The stars are not forever out of reach. We could go. We really could go. Here's my vision of our cosmic future. I imagine a time, perhaps a few centuries from now, when the first interstellar ships depart. Not dozens of people on generation ships, but thousands, maybe millions, on advanced fusion drive vessels. These pioneers would establish colonies on worlds around nearby stars. Each colony would develop its own character, its own culture, adapted to its environment. Some would be scientists, obsessed with understanding their new worlds. Some would be artists, inspired by alien skies. Some would be engineers, building new societies from scratch. And they would send back data. Not goods, not resources, but information, knowledge, ideas. Over time, these colonies would launch their own missions to even more distant stars. Humanity would spread like seeds in the wind, each new world becoming a launching point for the next wave of expansion. Within a few thousand years, humans could inhabit thousands of star systems. Within a few million years, we could fill the galaxy. And here's the beautiful part. Each world, each colony, would be doing its own thing, trying its own experiments, solving its own problems, creating its own art and culture and technology. The diversity would be spectacular. The creativity unleashed would be beyond anything we can imagine now. Some colonies might choose to modify themselves genetically, adapting to high-gravity worlds or toxic atmospheres. They might become separate species, but still recognizably descended from humanity. Some might merge with artificial intelligence, becoming post-biological entities of pure information. Some might remain stubbornly traditional, preserving old Earth cultures in isolated stellar enclaves. All of it would be humanity. All of it would be us, exploring every possible variation of what it means to be intelligent, conscious, alive. And through it all, travelers would move between worlds, trading not goods but stories. They'd be the immortals, aging slowly as they cross vast distances at relativistic speeds, carrying news and ideas between colonies separated by thousands of light years and millions of years of history. These travelers would be the living threads that bind human civilization together across the galaxy. They'd be the historians, the ambassadors, the witnesses to the grand sweep of our species' evolution. Maybe you, watching this video right now, have descendants who will be those travelers. Maybe some part of you, your DNA, your ideas, your influence, will cross the galaxy in ways you can't imagine. But even if humanity never leaves Earth, even if we fail to achieve interstellar travel, even if this is all just a dream, the fact that we can dream it, that we can understand the physics that makes it possible, that we can imagine ourselves among the stars, that itself is remarkable. We are the universe trying to understand itself. We are matter organized in such a way that it can contemplate the cosmos. We are, as far as we know, the only conscious beings in our light cone of the universe. That makes us precious. That makes us important. Not in a cosmic sense. The universe doesn't care about us. But in a moral sense, a meaning-making sense. We matter because we're the only thing that can make things matter. So here's what I want you to take away from these 3.5 hours. 1. The universe is stranger, more flexible, more accommodating to human ambition than you probably thought. Time is not absolute. Distance is not absolute. Reality itself shifts depending on your motion through it. 2. Humans really could travel across the galaxy in a single lifetime. The physics allows it. The only question is whether we'll develop the technology and the will to actually do it. 3. You are living in a pivotal moment in cosmic history. The decisions made in the next century or two will determine whether life remains confined to Earth or spreads across the stars. 4. You matter. Your choices matter. Whether you actively contribute to space exploration or simply maintain a sense of wonder about the cosmos, you're part of this grand story. Let me end with this thought. Right now, somewhere in the galaxy, light that left Earth during the Renaissance is arriving at distant stars. In that light is encoded everything happening on Earth in the 1500s. Every exploration, every work of art, every human drama. In a few centuries, light leaving Earth right now, light that carries the image of you watching this video, will reach those same stars. You are literally sending a message to the cosmos just by existing. Your light is spreading outward at 186,000 miles per second, carrying information about this moment in time, this version of humanity, this instant in cosmic history. And if we become a spacefaring species, if we develop interstellar travel, then someday, maybe thousands of years from now, human travelers might catch up to that light. They might look back at the photons encoding this era and see evidence of their ancestors, of us, taking the first tentative steps toward the stars. That's how far humans can travel through space in one lifetime. As far as we dare to dream, as far as physics allows, as far as our courage and ingenuity can take us. The stars are calling. The universe is open. The journey awaits. All we have to do is go. Thank you for joining me on this journey through the physics and philosophy of interstellar travel. If this video changed how you think about space, time, and humanity's cosmic future, please share it with someone who needs to have their mind blown. Hit subscribe if you want more deep dives into the big questions about our universe and our place in it. And remember, you're made of star stuff, traveling through the cosmos on a tiny world, capable of understanding the very laws that govern reality itself. That's pretty amazing when you think about it.